Hello, future engineers, innovators, and world changers. Bill Nye here. Today we're diving into the fascinating world of electrochemistry. It's the fundamental science behind the electricity that powers your phone, that keeps you connected to the world. It's what gets your car moving, and it's the key to unlocking the groundbreaking inventions of tomorrow. Electrochemistry is the essential link between chemical reactions and electricity, a dynamic duo that shapes our world. It's not just a connection, it's the very spark of our modern world, igniting progress and innovation. It's the reason why batteries work, storing and releasing energy on demand. It's how we precisely measure acidity, ensuring quality and safety in countless applications. And it's even how we prevent rust, protecting our infrastructure and extending the lifespan of valuable materials. By deeply understanding how electrons move and interact through chemical processes, we unlock revolutionary new ways to create, efficiently store, and sustainably use energy for a brighter future. Our journey today will cover the fundamental basics of electrochemistry, laying a solid foundation for further exploration. We'll explore essential lab techniques like titrations, mastering the art of precise chemical analysis. We'll uncover the hidden secrets of batteries, understanding how they power our portable world. And we'll catch a glimpse into the exciting future with fuel cells, a promising technology for clean energy. We'll break down complex ideas into simple, bite-sized pieces, using clear analogies, step-by-step guides, and engaging thought experiments to make learning easy and fun. By the end of this journey, you'll not only be well prepared for your exam, acing it with confidence, but you'll also gain a profound understanding of how electrochemistry elegantly connects everything, from the intricate workings of tiny sensors to the vast and complex architecture of massive power grids that keep our cities running. So, let's get charged up, ignite our curiosity, and dive headfirst into the electrifying world of electrochemistry. The world is eagerly waiting for your bright ideas, your innovative solutions, and your contributions to a more sustainable future. Let's start with the very foundations of electrochemistry. We're going to explore the key components and concepts that drive electrochemical reactions. Understanding these basics is crucial before diving into more complex applications. Electrolytes, electrodes, and redox reactions. These three elements are the building blocks of electrochemical cells and processes. An electrolyte is a solution full of ions, charged particles that move freely within the solution. These ions are essential because they carry electricity, acting like a highway for charge to flow between electrodes. Without electrolytes, nothing flows. The circuit remains incomplete, and no electrochemical reaction can occur. Electrodes are the entry and exit ramps for electrons, solid conductors, usually metals or graphite, that provide a surface for electron transfer. Every electrochemical cell has two: the anode, where oxidation happens, which is the electrode where electrons are lost by a substance, and the cathode, where reduction happens, the electrode where electrons are gained by a substance. Remember, oxidation at the anode, reduction at the cathode. This simple mnemonic will help you keep the processes straight. Redox stands for reduction-oxidation. One substance loses electrons, oxidation, another gains them, reduction. These two processes always occur together. Think, Leo the lion says jur, lose electrons, oxidation, gain electrons, reduction. Another helpful way to remember the relationship between electron transfer and oxidation states: the oxidized substance is the reducing agent. The reduced one is the oxidizing agent. They facilitate the electron transfer process. Picture a zinc and copper setup. Zinc at the anode loses electrons, becoming zinc ions in the electrolyte. This is oxidation in action. Electrons travel through a wire to the copper cathode, where copper ions gain electrons and become solid copper. This is reduction, completing the circuit. The electrolyte lets other ions move to keep everything balanced. This maintains charge neutrality and allows the reaction to continue. This is the dance of chemistry and electricity, how batteries and so many devices work. Electrochemical principles are at the heart of many technologies we use every day. Electrochemistry is all about controlling this flow for useful work. By manipulating these reactions, we can generate electricity, synthesize new materials, and much more. Master these basics, and you're ready for the next step. With a solid understanding of electrolytes, electrodes, and redox reactions, you'll be well equipped to tackle more advanced topics in electrochemistry. Let's see how we use these ideas in the lab. We'll explore some practical applications and experiments that demonstrate these fundamental concepts. Time for some lab action. Conductometric titration. Here, we measure how well a solution conducts electricity as we add a titrant. The more ions, the higher the conductivity. Example: titrating hydrochloric acid with sodium hydroxide. As you add base, hydrogen ions react with hydroxide to form water, a poor conductor, so conductivity drops. When all the acid is neutralized, adding more base increases conductivity again, thanks to extra sodium and hydroxide ions. If you plot conductivity versus volume added, you get a V-shaped graph. The lowest point marks the equivalence point. The reaction's done. It's a precise, visual way to track chemical reactions. Conductometry turns invisible chemistry into clear, measurable data. That's the power of electrochemistry in the lab. Let's check out another technique. Next up, potentiometric titration measuring voltage instead of conductivity. We set up an electrochemical cell and track the voltage between two electrodes as we add titrant. One electrode responds to the ion we're interested in. The other is a stable reference. As the reaction progresses, the voltage changes, reflecting the shifting balance of ions. Example: titrating iron 2 with cerium 4. At first, voltage changes slowly. Near the equivalence point, it jumps sharply. That sudden spike signals the reaction's completion. Plotting voltage versus titrant volume gives a curve with a steep jump. The equivalence point is right in the middle. Potentiometry is sensitive and works for many types of reactions. It's like having a high-precision meter for chemical change. With these tools, you can analyze reactions with incredible accuracy. Now let's see how pH fits into the picture. Let's talk pH titration, a classic but with an electrochemical twist. Here, we use a pH electrode to measure hydrogen ion concentration as we add base to acid. The electrode's glass tip senses H+ ions, converting their concentration into a voltage, which the meter displays as pH. As you titrate, pH rises slowly, then shoots up near the equivalence point. The steep jump marks where all the acid is neutralized. After that, adding more base raises pH slowly again. Plotting pH versus volume gives an S-shaped curve. The inflection point is the equivalence point. pH titration is a powerful way to analyze acids and bases. It's simple, precise, and shows electrochemistry in action. Now let's see how these principles power our world. Let's talk batteries. These compact powerhouses are the unsung heroes of our modern lives. They are the ultimate electrochemical devices. A battery is a self-contained cell, a miniature chemical reactor, if you will. It's a clever device that turns stored chemical energy into the electricity we need to power our world. Inside, you have an anode, the negative electrode. This is where oxidation releases electrons, setting them free to do work. Then there's a cathode, the positive electrode. This is where reduction consumes those electrons, completing the circuit. And an electrolyte, a crucial component. It acts as the ion highway, allowing ions to flow between the anode and cathode. A separator keeps the anode and cathode apart. It's a critical safety feature to prevent short circuits and potential hazards. Connect a device and electrons flow from a node to cathode through your gadget, creating an electrical current. Powering it, bringing it to life. The process continues until the chemical reactants inside are depleted and run out of steam. There are two main types of batteries that you should be aware of. Primary batteries, which are single-use, like your standard AA batteries. And secondary batteries, which are rechargeable, like the lithium-ion battery in your phone. Primary batteries can't be recharged. They are designed for one-time use. Once spent, they're done, their energy completely exhausted. Secondary batteries, on the other hand, can be recharged by reversing the internal chemical reaction. This clever trick lets you use them again and again, saving resources and reducing waste. Batteries are everywhere, portable, reliable, and absolutely essential to our modern lives. Their specific chemistry determines their performance characteristics and how we best use them. Next, let's dive deeper and compare some of the most common battery types available today. Which battery is the right choice for the job at hand? Let's explore the options and find out. Not all batteries are the same. Let's compare three big ones: alkaline, lead acid, and lithium ion. Alkaline batteries: zinc anode, manganese dioxide cathode, potassium hydroxide electrolyte. Cheap, reliable, perfect for remotes and clocks. Lead acid batteries, found in cars with lead and lead dioxide plates in sulfuric acid. Heavy, powerful, and rechargeable, great for starting engines. Lithium-ion batteries, the stars of modern tech. Laptops, phones, electric cars, graphite anode, lithium metal oxide cathode, lithium salt electrolyte. They're lightweight, high capacity, and rechargeable. During discharge, lithium ions move from anode to cathode. During charging, they go back. Alkaline is for disposable, low-power needs. Lead acid is for high current and durability. Lithium-ion is for portable, high-performance devices. Each battery is engineered for a specific job. Knowing their chemistry helps you choose the right one. The future? Even more advanced power sources. Let's look ahead. Enter the fuel cell, a game changer for clean energy. Unlike batteries, fuel cells generate electricity. As long as you supply fuel, no recharging needed. The hydrogen peroxide fuel cell is especially interesting. It uses liquid H2O2 at the cathode, which is reduced to water pulling electrons through your device. At the anode, a fuel like sodium borohydride is oxidized, releasing electrons. The result, continuous electricity, with water as the main byproduct. Fuel cells are quiet, efficient, and ideal for special uses like underwater vehicles or backup power. They convert chemical energy directly into electricity with minimal waste. This is the frontier of electrochemical engineering. As we seek cleaner power, fuel cells could transform how we energize our world. The future is bright and powered by chemistry. We've journeyed from the basics to the cutting edge of electrochemistry. It all comes down to controlling electrons and ions, redox reactions at the heart of every device. In the lab, titrations let us analyze reactions with precision. Batteries store and deliver energy in countless forms, each with unique chemistry. Fuel cells promise cleaner, continuous power for tomorrow. All these innovations are branches of the same scientific tree. The world needs your ideas. So go spark the future with electrochemistry.